Hello, men and women of science. This is Mr. Cochrane here to talk about stoichiometry calculations involving energy and chemical reactions. All stoichiometry calculations with energy need a balanced thermochemical equation, and they use mole to energy ratios from that balanced thermochemical equation. Thermochemical equations include delta H values. Delta H values represent thermochemical energy change in a reaction. The sign on the delta H value, either positive or negative, indicates whether energy is absorbed or released in the reaction. If delta H is negative, then the reaction is exothermic and it releases energy. If that occurs, then you place the energy as a positive value on the product side. If the delta H value is positive, then the reaction is endothermic, meaning energy is absorbed. If that is the case, then you would put the energy value on the reactant side. So the following thermochemical reaction has a delta H value of negative 822. This is the reaction for the formation of rust. Since the delta H value is negative, then we would put 822 kilojoules, kilojoules is a unit of energy, over here on the product side. So all stoichiometry calculations with energy would start with that balanced thermochemical reaction. And to balance this reaction, we add coefficients of 4, 3, and 2 there. And you'll notice that we have our 822 kilojoules. As I said, kilojoules is a unit of thermochemical energy we use in science. A more familiar unit to you would be the calorie. 1 kilojoule is equal to about 0.239 food calories. This equation then shows that 4 moles of iron reacting with 3 moles of O2 produces 2 moles of iron 3 oxide and 822 kilojoules of energy. So the coefficients give us the relative amounts of each substance in moles, and it shows us how they relate to energy change in kilojoules. So let's try a stoichiometry conversion involving both moles and kilojoules. When we do that, we're going to use mole to energy ratios from the balanced equation. So what is a mole to energy ratio? Well, if you look at this equation, the coefficients, remember, tell us the moles. So we can look at mole to kilojoule ratios or kilojoule to mole ratios in any combination. 3 moles of oxygen, for example, produce 822 kilojoules of energy, so we would have a 3 mole to 822 kilojoule ratio, or 822 kilojoules of energy are produced at the same time as 2 moles of iron 3 oxide. And you can see there would be many other ratios from this equation. So let's try a kilojoule to mole problem and see how we reduce these ratios. Here's a question. How many moles of iron metal are needed to produce 523 kilojoules of energy if the delta H value is negative 822 kilojoules? Here's our balanced thermochemical equation showing our kilojoules as a product. And this time it's useful to identify what we are converting from, as always, and what we are converting to. In this case, we are converting from kilojoules to moles of iron metal. And so we're going to write down our 523 kilojoules. Remember, it's important to include the unit. And we can go right to our equation because we know that, according to the equation, we have 822 kilojoules of energy for every 4 moles of iron. We use 4 moles of iron here because that's our desired value. The units, kilojoules, factor out, and we can go right to our calculator. We're going to multiply 523 times 4 divided by 822. The only units we didn't factor out here, moles of iron, is what we wanted. And we round that to 3 significant figures, as 523 has 3 significant figures. And then, like all good Stoich calcs, you're going to circle your answer. All right, let's kick it up a notch. Let's try some Stoich with mass in it and energy. Stoichiometry calculations with mass and energy use ratios of moles to energy from the balanced equation like before, but this time, in order to use that mole to energy ratio, we might have to convert either from moles to grams or grams to moles to access that ratio. So let's try a gram to kilojoule problem here. How many kilojoules of heat are released along with 270 grams of iron 3 oxide? There's our balanced equation. Again, we want to identify what we're starting from or converting from, in this case 270 grams of iron 3 oxide, and we want to find how many kilojoules of heat are produced. So the first step with all these Stoich calcs is to write down what we're converting from. make sure that we include both the unit, grams, and the substance, iron 3 oxide. Students who have trouble with these calcs often forget to record those. Since we want to use the mole to kilojoule ratio from the equation, we need to convert our grams to moles. In order to convert grams to moles, we need the molar mass. 1 mole of iron 3 oxide has 2 moles of iron atoms and 3 moles of oxygen atoms. So we would add up the mass of 2 moles of iron atoms to 3 moles of oxygen atoms and get a molar mass of 159.7 grams. We would put that then into our mole ratio. Remember, the molar mass is the grams equal to 1 mole of a substance. Be careful not to use the coefficients from the balanced equation here yet. And we have now factored out grams and converted it to moles. Now that we have moles of iron 3 oxide, we can go ahead and access the kilojoule to mole ratio from our equation. In our equation, we have 2 moles of iron 3 oxide, and we have 822 kilojoules. Notice that moles of iron 3 oxide will factor out now, and we are left with the units kilojoules, which is what we wanted to find here. So it's time to grab our calculator and crunch some numbers. You remember, when you put these values into calculators, any numbers on top you'll multiply by, any numbers on bottom you'll divide by, and if we crunch those numbers and round to 2 significant figures like our starting value, you can see that we end up with 690 kilojoules. So to summarize, to solve a problem with energy, you're going to start with a balanced thermochemical equation. You're going to write down the initial value with proper labels. If the initial value is in grams, we're going to use the molar mass ratio to convert to moles. If the initial value is moles or kilojoules, we get to skip that step. We're going to choose the mole to energy ratio from the balanced equation that factors out the units that we're getting rid of and gives us the units we want. If we want our final answer in grams, we would use molar mass to convert to grams, but if our final answer is just in moles or kilojoules, then we get to skip that step. We're going to enter the numbers in our calculator and round to the proper sig figs, then circle our answer. So here's a set of problems you can try. Pause this video for a moment and then try these problems. Make sure you write everything down as you saw in the examples, and then when you restart the video, you can check your answers. They'll be displayed. If you have trouble, you can rewatch the video again, or you can come in and check with your teacher. Bring your work with you when you do. Go ahead and pause the video now. So here's the answers to these questions. Check your work, check your significant figures, and again, if you need help, go back and watch the video again or come in and talk with your teacher. This is Mr. Cochrane signing off.